Here is another problem. It says measurements of a nickel cylinder are shown in the following figure. How many significant figures should be reported in the density calculated from these measurements? This seems very tempting. It seems like you are going to want to plug these into a calculator and get a number. But notice how the answer choices are all asking you how many sig figs should be reported. They're not asking you to calculate density or volume. It's important that you understand the relationships between these values though. So let's talk about that actual relationship and build it out intuitively. Density is equal to mass over volume. We are given the mass here, and we have the volume equation, which is pi r squared h. Pi times the radius squared times the height of the cylinder. We can look at all of these values and find out how many sig figs there are using the rules of sig figs. The rules of sig figs say that if there's a decimal point, leading zeros never matter. Interior zeros, which are zeros between some non-zero digits, those do matter. And any zeros on the tail do matter for when there's a decimal point present. All of these have decimal points. So we follow the rules and we find that there are 4 sig figs here, 5 sig figs for the height, and 5 sig figs for the mass. When it comes to doing multiplication and division, the rules are relatively simple. Find out how many sig figs are involved in your operations and go with the lowest number. It's the weakest link rule, as I call it. The part of your mathematics that has the lowest number of sig figs is the weakest link. It's the one where you're just least certain about like the value of it compared to the others. So what we're going to do, I'm going to replace all these values with how many sig figs they are. But something to keep in mind is that we oftentimes round pi to 3.14 or 3.14159 or whatever. Right here it says assume that pi is exact. So pretend like you put pi into the calculator and it gives you infinite digits, every digit that exists if we were to know it. All this is saying here is that we are not concerned about the number of sig figs that pi has, because pi has an infinite number of sig figs if they were all known. It just goes on and on. So we don't care about it. Ignore it. I'm going to replace the mass. Actually, no, I'm going to do this. Duplicate's like one of my favorite tools. So I'm going to replace these values with how many sig figs there are based on what we have here. The mass has 5 sig figs. The pi is just pi. The radius has 4 sig figs. These are not values, by the way. Just want to make sure that's clear. And then the height has 5 sig figs. Looking at this, we're evaluating these, and we see that the weakest link is the number of sig figs here. The radius is only 4 sig figs. It's the weakest link. So since that part of our calculation is just 4 sig figs, that means you're going to report just 4 sig figs. I need to reiterate, these are not the values of the dimensions of the mass or the height or the radius. This is just putting the sig fig count in and seeing that the weakest link is the 4 sig figs that is held within the radius. Therefore, your answer is 4 sig figs. So you could totally do the actual math. I don't want people thinking this is a calculation, but you could totally do the actual math and get some long string of numbers, and you would report just 4 of those digits. This question here is really intimidating. And if you get something like this is going to be really testing your knowledge of dimensional analysis. It's just a really intense problem. But if you want to score high, then you might want to learn how to do this. So there's a lot going on in here. City water supplies are fluoridated by adding sodium fluoride to the water. If you live in a city of this many people, 1.2 times 10 to the 5 people, and each person drinks 650 liters of water per day, what mass of sodium fluoride must be added to the water supply each year? So that's the first thing I want to kind of highlight, is that all of these are per year. That's missing from the answer choices, but it's really helpful if you recognize that you're already dealing with a rate. These are all per year. And that's why each year is underlined, because ultimately your dimensional analysis is going to depend on you recognizing that you're dealing with a rate. In order to have the required fluoride concentration of 1 kilogram of fluoride per 1 times 10 to the 6 kilograms of water. And Luckily, you're given that sodium fluoride is 45% by mass of fluoride, and the density of water is 1 gram per milliliter. This is an intense problem. You couldn't just Google that and get an answer, so that's why I think chemistry and physics courses are valuable, because they teach you how to think about things that aren't just Googleable. So here's what we're going to do to start off. To do this, I personally would start off with how many people there are. There are 1.20 times 10 to the 5 people. And that makes sense. I mean, it's just starting off with people. It's kind of like one of the first things that makes sense. There's a lot of people in this city. Not even a million, but there's enough. So I'm going to get rid of people. And I'm going to go to liters per day. And I'm going to fix this in a bit, but this is really just about learning to move one step at a time for dimensional analysis. So we have 1.20 times 10 to the 5 people. And over 1, I'm multiplying that because every one person consumes 650 liters of water per day. I have a rate within a rate, so to speak. It's in the numerator, so it's like a fraction in a fraction here. Liters per day, that might be a little confusing leaving it like there, so this trick works. That is actually its own little conversion factor. I'm going to move the day, which was right here, right? I'm going to move it to just being a denominator like this. It works the same way. So let's do some cancellations to see where we are so far. People have been converted into liters. And this is liters of water. So if you really want to be specific, I do recommend you put units. And we're not going to end up with liters ultimately, so you don't want to circle it to be done with it. This is just showing you how your units are canceling. And so far, these are only units that canceled, people. So look at your problem again and think, well, what do we have here? Currently, we know how much water the city uses per day. Matter of fact, if you were to do your dimensional analysis, you'd find out that if there are this many people and they drink this much water per day, your units as they stand now are simply how many liters of water per day the city uses. Not the answer that we're looking for. So keep moving. Also, something interesting is, just in case you didn't know, a year has 365 days. So maybe right now you want to get rid of days. Since days is in the denominator here, you want to put days in the numerator next door. We're going to go from days to years. And we know that there are 365 days in 1 year. Let's evaluate our units as they stand now. If we were to do the math here, we'd currently be left with liters per year. So doing the math, we'd find out how many liters of water this city uses in a year. And you can kind of feel in your heart we're getting closer to the answer. So dimensional analysis will actually get us all the way there. So currently, we have liters of water. It's in the numerator right here. So if we want to kill liters of water, we put it in the denominator. We're going to go from liters of water to, there's a lot of it might be a little confusing, well, what is it going to be? Liters and milliliters of water are going to be expressed using your knowledge of metric prefixes. So I can go from liters of water to milliliters of water if I wanted to. And that might be reasonable. So 1 liter is 1,000 milliliters, whether it's water or some other liquid. Currently, liters of water have canceled, and we're with milliliters of water. Here's why the density of water comes in, even though it's a relatively easy number, it's just 1, is because we're going to go from milliliters of water to grams of water. And I'll show you why that works in a second. But we have a really easy number here. 1 gram of water is equal to a milliliter of water. That's the density of water. So this conversion factor is simply the density of water. It helps you connect mass and volume for water. Now, canceling out our units. Again, we currently have how many grams of water this city uses up in a year. Definitely not the answer we're looking for yet. But we can continue moving toward it, because the thing about dimensional analysis that can be a little tricky is that you're going to go into the unknown, and that's fine. You have to take it one step at a time. So we have grams of water in our numerator. It might be like, well, what are we even doing? If you don't know, that's okay. Just put it in just cancel it out and see, just keep moving. That's how I feel about it. So we have grams of water here. Oh, this might be useful. Um, we have a mass of water in its relationship to a mass of fluoride. Matter of fact, it might just be helpful if I go from grams of water to kilograms of water, because I know that 1 kilogram of water is 1,000 grams of water. That helps me get rid of grams of water, and I currently have kilograms of water. Thinking logically about all the things that canceled and what hasn't, we currently have kilograms of water per year. So we know the mass of the water that the city uses every year, and we're working in the right direction. This is a very long problem. So currently we have kilograms of water, we don't want kilograms of water. But something really cool happens now. We have a relationship between kilograms of water and kilograms of fluoride, so we're finally getting to the chemistry aspect of it. Kilograms of water, we're going to go from kilograms of water to kilograms of fluoride, which I'm going to write as F minus, because that's the fluoride ion. And we have a relationship in this conversion factor. 1 kilogram of fluoride is necessary to properly fluoridate 1,000,000, which is 1 times 10 to the 6th, kilograms of water. That cancels kilograms of water, leaving us with kilograms of fluoride. Very tempting to call yourself done, but you're getting there. We don't just put fluoride ions aren't just free floating. Ions don't just float like that in the world unless they are part of an ionic compound or they're dissolved in an aqueous solution. So in this case, those fluoride ions are going to be held within NaF, which is an ionic compound that when it dissolves creates sodium ions and fluoride ions. You care about the fluoride ions. This is not really testing your knowledge of percent composition or percent by mass, but it's helpful to know that if you were to dunk in, let's say 100 kilograms, if you were to drop one big 100 kilogram chunk of sodium fluoride, which is a solid, into water and it completely dissolves, this 100 kilogram chunk is going to only become 45 kilograms of fluoride ions floating around. Of course, the other 65 or 55 kilograms is owed to the sodium. So if you wanted to work it out, the percent composition of sodium fluoride by mass is 45% fluoride. That's going to be you could figure that out if you weren't given it, but at least this long problem was nice enough to give us that. So we're going to put kilograms of fluoride, and we're going to put kilograms of NaF. Keep in mind that the problem is asking us about sodium fluoride, which is NaF. So we're actually at the end of the problem now. This right here is just a ratio. We are not given the actual mass, that's what we're solving for, of the sodium fluoride we need. But we know a ratio. We know that, and you can use any ratio that makes sense, any numbers. Let's just say we have 100 kilograms of sodium fluoride. 45 kilograms of that would go to the fluoride ion. The reason that I chose 145 is just because we know that 45 is 45% of 100. You could have also chosen to put a 1 and a 0.45. It's literally the same thing. You could have put 1,000 and 450. We can do division, and we see that 45 is 45% of 100. And that gives us our final units. And when you do your math here, be very careful with your parentheses. You will get the right answer. Because ultimately, what are the units that survived? The units that survived are the year in the denominator and the kilograms of sodium fluoride in the numerator. So your answer is whatever number of kilograms of sodium fluoride per year. And that's why I said that the per year is kind of implicit, and that's why it's underlined here. It's helpful for your dimensional analysis to relate that to the time. This question says, which of the following compounds is or are incorrectly named? So this is going to test your knowledge of a lot of things. First of all, you need to know the difference between ionic and covalent or molecular compounds. I don't see any acids here, so I would also recommend you know how to name acids, which is dependent upon your knowledge of covalent compounds. and you need to know how to deal with transition metals. Transition metal naming is a little bit of a beast because it's a subset of ionic naming. So let's see how that works here. In this problem, we're looking at the first one, the second one, we're looking at it one by one. Look at the first one. Dimanganese heptoxide. Is that the name for this formula? It is not. And the reason is this is ionic. So I'll actually write that here. This is an ionic compound. For ionic compounds, you are not permitted to use prefixes that are numeric. So you wouldn't say dimanganese heptoxide. You would just call it manganese 7 oxide because that would be the name of this ion. So because that name doesn't match, because the name does not match the formula, you would definitely say that one is out. One is not correct. One is not correctly named. It is incorrectly named. Oh, and that's also something important to read. When you're doing it, read carefully. It says which of the following compounds are incorrectly named. So actually I will circle this because it is incorrectly named. That's probably a really big way people can mess up is even I was just reading it too quickly. Because you're marking the ones that are incorrectly named, one better be in your answer. It's easy to pick the ones that are correctly named. Take a look at the second one, sodium chloride. This is also ionic. And because it's ionic, you don't use numerical prefixes. And there are none. So this is actually correctly named. The next one is Al2S3. Is that aluminum sulfate? Sulfate is one of the polyatomic oxyanions. Polyatomic means more than one atom, and then oxy means has oxygen, and anions means it's negatively charged. So if you're looking at this, Al2S3 would actually be called, actually right here. It's also ionic, by the way. The real name would be aluminum, because you just name the first thing, and that's a metal, so it's just aluminum. Aluminum is not a transition metal, so there's no need for parentheses or anything. And then you move on to the anion, which is a single negatively charged. Of course, there are 3 of them, but it's the actual ion itself is just a sulfide ion. It's not sulfate. It's not sulfite. This is a sulfide ion. This is a sulfate ion, and this is a sulfite ion. So you definitely need to know your polyatomic ions and some mnemonic devices. There are those that can help you out with that. So because S is sulfide and not sulfate or anything, this is definitely incorrectly named. Here's the correct name. And we would say that because it's incorrect, we're going to circle it. So that means it should appear in your answers. Moving on to the next one. This also involves knowledge that you recognize a few different things. Cobalt is a transition metal, which means you do need those Roman numeral parentheses. So far so good. We got the cobalt. It has parentheses, so we know we need them. You will need to be able to verify whether the oxidation state 2 is correct or not. So here's how you do that. Here's one way to do it. You can write out CO NO2 2. That's the formula. Break it apart. So first, you have cobalt. So you know that it's cobalt with some charge. You don't know what the charge is explicitly. You can verify that, but at least you know it's going to be cobalt something. This mystery box is the charge on the cobalt, or the oxidation state. This mystery open parentheses is going to be the same information. Do we know the charge on the cobalt? Not explicitly. So you leave it alone, and you come back to it. So you look at the NO2. There are 2 of them, so you can do 2 times the NO2. Every NO2 is negatively charged. You do have to know your polyatomic ions. This is nitrite, not nitrate. So this NO3 minus is nitrate. NO2 minus is nitrite. When you hear the "ite" ending, that means you lost an oxygen relative to the normal form. So normal load nitrate, NO3 minus. Nitrite has 1 less oxygen. The charge will be the same. That's true for all of those declinations. So that's just nitrite. Now, for answering the question, that's plenty. But if you really care about finding out the oxidation state of the charge, which you'll eventually have to do, as you will in some of these questions, then you'll have to look at this and kind of do a little bit of thinking about the charging. So there are two nitrate ions in one formula unit. We know that every nitrite ion is -1, and there's two of them, so there's a total of -2 charge. Now this is an overall this compound is neutral. So if there is a -2 charge from the anion side, then the cation side better have a +2 charge in total. And there's just one cobalt ion in the formula, so this single cobalt ion has to be a 2+. And that's why it's cobalt 2 nitrite. That is correct. So this is a good name. And then number 5, aluminum, not a transition metal, does not need parentheses. And then is P phosphide, or maybe it's phosphate or phosphite. Again, to kind of verify, you can look at it this way. If it's a single ion, then it's going to be the "ide" ending. In this case, it's phosphide. So not single, but if it's monatomic, but it's not hydroxide, so it's like just a general "ide" ending, that's going to be P3 minus. If it were PO4 3 minus, that would be phosphate. Notice that 8 ending gives you a clue that there's some oxygens in there. And if it were PO3 3 minus, we lost an oxygen from this normal 8 ending, so it's not phosphate, it'd be phosphite. But it's neither of those. It is actually just a phosphide, so it is aluminum phosphide, so that is correct. Which means it should not be chosen. So your answer, since it's asking which ones are incorrectly named, it is just 1 and 3. 1 and 3 are wrong, the others are right. This question says calcium hydroxide, which is this first, actually no, it's the second thing, the last thing, sorry. Calcium hydroxide is a compound used in dentistry, blah, blah, blah. Here's the reaction. You have 101 grams of water, and it reacts with excess calcium oxide, but it produces calcium hydroxide. But the percent yield of this problem is 88, or the percent yield of this reaction is 88%. Percent yield basically is like this. Let's say I invite 200 people to my party. I send out 200 invites. That's my theoretical yield. In theory, 200 people should show up. Now, if 120 people show up, that's my actual yield. That's how many people actually came. So you do your division, and you'll find that percent yield is simply equal to the actual yield divided by the theoretical yield times 100. In this case, that would be 120 people divided by 200 people who should have come, or theoretically would have come, times 100, and you get 60%. Naturally, reactions are going to have random things that are going to cause them to not always be 100% yield. Just like if I invite 200 people, 80 people might have things come up. Oh, I got to wash my hair, I got to watch my kids, whatever. So just recognize the equation for percent yield, and please don't get it mixed up with the equation for percent error. That's a big problem that people have. So here's the equation for percent yield. Now, another thing that's really important is that in order to get the theoretical yield, you must do stoichiometry. So let's do that. We have 101 grams of water and excess calcium oxide. There's excess calcium oxide, so you don't really need it in terms of mathematically. Like, you don't know how much there is. It could be like 1,000,000 grams. You just won't run out of it. Also, what's really nice is that in this case, you're given the molar masses. So you don't have to calculate them from the periodic table, but you do need to know how to calculate molar mass in general. So we have 101 grams of H2O. And as I say, put your starting thing over 1, because that's all you know right now. You have 101 grams of water. Oh, by the way, step 1, what we're doing right now, we're finding the Ty. That's why I'm putting in parentheses. Step 1 is do stoichiometry. That gives you the theoretical yield. How much should you make in a perfect world where every molecule does exactly what it's supposed to do? I'm going to go from grams of water to, in this case, moles of water. You always want to turn things into the mole if you are not given moles. So I'm turning my grams of water into moles of water using the molar mass as my conversion factor here. So molar mass, that's your conversion factor. It's helping you go from grams to moles, and also can help you go from moles to grams. We are given the molar mass of water. It's actually 18.02. So 1 mole of water has a mass of 18.02 grams. Then you keep moving along, crossing out what you don't need anymore. If I were to stop the problem right here, it would literally just be a molar conversion from grams to moles. But moving on though, we don't care about moles of water. What we do care about is going toward our other chemical, and that's going to be our product here, which is calcium hydroxide. So that's going to be this information here. So I guess I'll color code that. Moles of CaOH2. This OH ion, by the way, that's called the hydroxide ion. It's one of the polyatomic ions you do need to know. Now, what's the relationship here? Like, what do you do when you have moles over moles? Moles of something over moles of some other thing in your dimensional analysis. Really important that you recognize that when you have moles over moles, you got to use the balanced equation. This was already balanced, and it turns out that the coefficients in front of all of them is just 1. 1, 1, 1. So that means that if you're looking at your equation, you're going to use a 1 and a 1. The 1 on the top came from over here, and the 1 on the bottom came from over here. If they weren't 1, 1, 1, like if they were like 2, 3, 4 or whatever, you'd use those numbers, but this reaction is balanced as written. If it isn't balanced, balance it before you just assume it's 1. But this happens to be balanced as 1, 1, 1. Okay, so once you have those coefficients, then you move on. Moles of water is gone, and you have moles of calcium hydroxide. We don't want moles of calcium hydroxide, we want grams of calcium hydroxide. So we're going to put grams of CaOH2, convert that into moles of CaOH2. For a second, I want you to recognize that you always need to have units, or a value, units, and the chemical as often as you can. Because notice how we have grams of water here, and we're turning that into moles of water, then moles of water into moles of another thing, and then I flipped that on accident. Move that down here. It's actually a perfect example of why you should write your units out, because you can catch mistakes before they actually hurt. So when I'm canceling out my units, I have moles over here on the top for calcium hydroxide, which will cancel with moles of calcium hydroxide on the bottom. And then this is where you ask yourself, okay, what's going to go in this conversion factor? How do I relate grams of this substance to moles of this substance? Well, I have the molar mass. Turns out that 1 mole of calcium hydroxide has a mass of 74.10 grams. And then you do all that and you get your answer. So that's going to give you some number for your theoretical yield. And I just need to emphasize again that that's your theoretical yield. When you do stoichiometry and you get your theoretical, and you get that number, that's your theoretical yield. How much would there be if everything works out just perfectly? So I'm going to do the calculation live with you. It's 101 times 74.10, dividing that by 18.02, and I get about 415.3. We're not worried about suffix here really, because it's multiple choice. So that's my theoretical yield. Then step 2 is set up your percent yield equation. Percent yield, actually the equation is already up here at the top, so I'll just start filling in the pieces. We know the percent yield is 88. So 88% is the percent yield. It's equal to the actual yield, which is what we care to find. That's what you're looking for. It's equal to the actual yield divided by the theoretical yield, which we actually just found as 415.3-ish. Notice that 415 is an answer choice. That's a gotcha thing. If somebody were to do the stoichiometry and think, oh, there it is, That's how many grams of calcium hydroxide I could make with an 88% yield. That's not true. This is the theoretical yield. Don't choose that answer. And part of the equation is multiplied by 100. So you just got to do algebra here. You made it to tech because you know algebra. So you're going to divide 100%. You divide 88% by 100. You get 0.88. So if I kind of unpack this, to turn a percent into a fractional amount, you just divide by 100. That's why we get 0.88. Then you multiply both sides by 415. That cancels it over here. Boom. And that's going to be, oh, thought I erased that. And that's going to be your actual yield when you do the math. So it's 88% of 415, basically. And I believe that's 365. So that's how you do that one. This question, number 8, is asking, what is the name of HClO3? You've got to know your polyatomic ions. So let's take this HClO3, or not HClO3, HClO, sorry. I was thinking about where it came from because the trick I'm going to show you is related to that. So HClO is made of the H plus ion, which is what makes it an acid, as well as this polyatomic oxyanion, which is ClO minus. So if you learn your polyatomic ions, this is not chlorate and it's not chlorite. Let's actually take a look at that. So Cl minus, that's chloride, like sodium chloride, which is the salt we put on our food. That is Cl minus. That's a monatomic anion. It's just a single atom, a Cl ion. Now, if you have ClO3 minus, that's one of the polyatomic ions you do need to know called chlorate. Don't get it confused with the other forms of it. Suppose that you add an oxygen, so plus 1 oxygen. If you add an oxygen, it would be ClO4 minus, which means it's going to have a new name. When you add 1 oxygen to the base form, which you do need to commit to memory, then it'll become perchlorate. The per prefix means 1 more oxygen. If you were to subtract 1 oxygen, so minus 1 oxygen, then it gets a new ending. So first of all, the formula would be ClO2 minus, and that's going to be called chlorite. And this pattern works for all the halogens, by the way. So bromate would be BrO3 minus. Bromite would be bromate minus an oxygen. So bromite would just be BrO2 minus. So just recognize those patterns and it kind of starts to fill in for you. Notice that this ite ending means you lost an oxygen from the base form. And then you can lose another oxygen sometimes. In this case, you actually have another oxygen to lose. So if you lose 2 oxygens, you've already used up the ite ending by itself. The ite ending means you lost an oxygen, so you can't call it chloride as well. You have to somehow indicate that this is less than chlorite. So it's going to be a name that's going to be hypo in front of it. This prefix hypo means less than. So hypochlorite is ClO minus. And that's actually the one that we have here. This is the hypochlorite ion. So with that in mind, it's going to be very helpful for you in naming the acid. So move that over here for reference. So this is a hydrogen ion and a hypochlorite ion. You have to know the rules for naming acids, but once you know the rules for naming acids, you can kind of think of this mnemonic device. If you ate ick, you get the ite us. Now it's a little bit weird, but think about the fact that if you eat, so if you ate something icky, right? Like you ate something gross, you ate ick, you get the itis, which is kind of like a disease, right? Like you just pretend like it's a disease. So what this means is if the ion ends in ate, then you add the ick ending, and they're all going to end in acid. So for example, sulfate. Now I'll do sulfate. I'll do nitrate. So this is the nitrate ion. The nitrate ion is NO3 minus. If I want to make this an acid, I'm going to add an H for every negative charge. Since there's one negative charge, I'm going to add one H. This is no longer a nitrate ion. This is nitric acid. So when we say like 8-ic, the 8 ending was replaced with ic, and then we add on the term acid. So that's why this is nitric acid. Now, what this is here is an ite ending. So you keep everything that's before the ite. So that's the hypo and the chlor. And you would actually call it hypochlor. And then the rest of it would come along, or the new ending is not going to be ic acid. It would be hypochlorous acid. And the reason that it's hypochlorous acid is because this ite ending tells us that we need to replace ite with us. So it's us acid. So hypochlorous acid is not the same as hypochloric acid, nor is it, or as chloric acid, nor is it the same as hydrochloric acid. So just know your naming rules for that, for acids and bases, or really just acids there. I like this question, number 9, because it makes you think about a few things. Number 9 says, a metal ion has 50 protons and 46 electrons. Let's handle that immediately. Because we know that ions are all about electrons being lost or gained. Nothing to do with protons. Nothing to do with neutrons. Neutrons being coming and going, so to speak. Not coming and going, but being different. That's going to give you isotopes. So this is an ion. Don't get it confused with isotopes. So if there are 50 protons, what you're going to do is look at the periodic table and find the 50th element. Remember, the number of protons tells you which element it is. The 50th element is 10, which is Sn. It has to be 10, because if it didn't have 50 protons, it would not be 10. So just remember that the number of protons is directly linked to the identity of the element. Now, if it were neutral, it would have 50 protons and 50 electrons, because we know that protons are positively charged and electrons are negatively charged. And if there are 50 protons and 50 electrons, so 50 plus negative 50, right? Because that's the charge on the electron, you get a neutral compound. But it's not. In fact, there are only 46 electrons here. So it lost 4 electrons. When you lose electrons, you actually have a net positive charge. So this is a 10-4 ion. So the way that you would write it, if you were to name it, would be, at least this part of it would be called 10 parenthesis I4 closing parenthesis. That is the 10-4 ion. We don't need the name, but just in case you were curious of how the name of this answer would be written. Then it says, well, it's going to form an ionic compound between, well, itself and whatever the heck is in the third period that's a halogen. So if you sketch out the periodic table, you'll find out, or if you look at the periodic table, I should say, you'll find that the third period, remember, periods are rows, the third period is going to be the third row, and then you also have the halogens. The halogens is the second to last. So over here, you'd have, okay, let me try that again. Over here, you'd have the noble gases. So the noble gases are headed off with helium, right? Blah, blah, blah. That's not the halogen family. The halogen family is all the enes. The halogen family starts with fluorine. And then you get, so the halogen family starts with, let me redo that. It starts with fluorine, then you get chlorine, then you get bromine, then you get iodine. That's the halogen. So you need to know the groups and the periods. Just remind you that periods go from left to right, so they're the rows, and then groups, also known as families, those are the columns. These colors mean nothing special. I was just drawing. But in the third period halogen is chlorine. So what that means is you have a chloride ion, Cl minus. And then you're looking at this and you think, well, how many chloride ions do I need to balance out the tin-4? And it's going to be 4 of them. So you do your crossover trick, or you just think logically about it, and your answer is going to be SnCl4. And if you did care, this is the chloride ion, not chlorate, not chlorite. Those would be the polyatomic thingies, wherever they went. So this would be called tin-4 chloride, and that would be your answer. And then we have a wonderful limiting reactant problem for number 10. It says, what mass of iron is produced when 225 grams of iron 3 oxide, which is this, and it's already balanced, so that's good. When 223 grams of iron 3 oxide, you're given the molar mass, react with 175 grams of carbon monoxide. This is a limiting reactant problem. And it's pretty realistic in the sense of, in real life, you can run out of one thing before the next. If you're making sandwiches, and each sandwich requires 2 pieces of bread, and it's a super simple sandwich. Say it's 2 pieces of bread and a tomato. That's a weird sandwich, but whatever. If each of your sandwiches requires 2 pieces of bread and a tomato, you know the ratio, what's required. So let's say you make 3 pieces of bread, 3 sandwiches, and then you try to make a 4th, but you run out of tomato. Well, this is not a complete sandwich. Notice how you have 1, 2, 3, 4, 5, 6, 7, 8 pieces of bread. So 8 breads. And you only have 3 tomatoes. Because each sandwich requires 1 tomato and you ran out, the tomato is your limiting reactant or your limiting reagent. It's what caused you to stop making more complete sandwiches. The bread is the excess reagent. It's the one that did not run out first. And notice how the total number of sandwiches you make is dependent upon the one that runs out, the ingredient that runs out first. That logic is the same for limiting reactants, except we have quantities that we have to deal with, so we're going to do stoichiometry. Sometimes these are called, or at least I call them, double stoichiometry, because you have to do stoichiometry twice. So this concept is sometimes combined with percent yield. So just make sure you understand percent yield and limiting reactants. So double stoichiometry says this. We're going to do stoichiometry twice. First, let's deal with the 225 grams of iron 3 oxide. We have a certain amount of iron 3 oxide that's available to us. Then we have another thing. We actually have 175 grams of carbon monoxide available as our other ingredient. So you're going to do stoichiometry with both of these. One of them will run out before you're allowed to make the maximum actual amount of your product, which is iron. So it's asking us to find out the amount of iron. Notice how in this reaction you also have carbon dioxide. Nobody cares. If you were given a spoken version of this reaction, kind of like you practiced earlier where you have to convert the words into an equation. Sometimes you'll have to convert words into an equation and then balance it. Luckily, this is given to us as an equation that's already balanced, so we're focusing just on the limiting reactant part. Let's do our first stoichiometry, which is dealing with the iron 3 oxide. When you do double stoich, you deal with one reactant and you ignore the other. So for the first one, we're going to ignore the carbon monoxide and deal just with the iron 3 oxide. So how much iron 3 oxide do we have? 225 grams of Fe2O3 over 1. Convert your grams of iron 3 oxide into moles of iron 3 oxide using the molar mass, which is given to us as 159.7. So 1 mole of iron 3 oxide has a mass of 159.7. Canceling your units, you want to keep moving. Now you're going to make a shift. We're going to go from moles of iron 3 oxide to moles of the product that we care about, which is going to be the iron. The ratio here is going to come straight from the balanced equation. We have a big 2 in front of iron and a big invisible 1 in front of the iron 3 oxide. That's where this 1 comes from. Remember, when you have moles of something over moles of something else, you use the balanced equation, the coefficients from the balanced equation to get that ratio. And then we're going to finish up our stoichiometry by putting moles of iron on the bottom and going from moles to grams by just finding out how many grams of iron we could make. If we have this much iron 3 oxide to start off with, and we're not worried about the carbon monoxide right now. So with this, we're going to use a molar mass of pure iron, which is on the periodic table. It was not given you, and that's the part that I find interesting, is that you're given 2 molar masses. You actually also need the molar mass of pure iron, which is 55.85. And then you cancel, and you're going to get some number. So if I do the math here, I get, let's see, 225 times 2 times 55.85, and that just came from memory. I'm dividing that by 159.7. And I get about 157, which looks right, I suppose, yeah. So 157 point, let's say about 4. And this is a multiple choice question, so it's going to be rounded to 3 sig figs. You can see that there. Grams of iron. Now, we just did stoichiometry, and we found out that we can make 154 grams of iron based on purely knowing this amount of the iron 3 oxide that makes it. We're not even worried about the carbon monoxide yet in the first stoichiometry problem. Keep that value in your pocket or on your paper because you're going to need it to reference. Because don't forget, we have to do stoichiometry again. This time, we're going to work with the carbon monoxide and we're going to ignore the iron 3 oxide. Now we're thinking to ourselves, okay, given this amount of carbon monoxide, how much iron could we make if we had extra iron 3 oxide? Unlimited or unknown, right? So do your stoichiometry again, and you're going to get 170. You're going to start off with 175 grams of carbon monoxide. Convert your grams of carbon monoxide into moles of carbon monoxide using the molar mass, which is given to us as 28 grams per mole. Grams carbon monoxide cancel. Convert your moles of carbon monoxide into moles of iron. And the relationship between that is there's a big 2 in front of iron and a big 3 in front of carbon monoxide. So you put 3 in front of the moles of carbon monoxide, 2 in front of the moles of iron, just like you did any other time. And you can do some cancellations here and here. And then you're going to convert your moles of iron into grams of iron. And whenever you convert moles to grams or grams to moles, you need to use the molar mass. We are given, or we find the molar mass of iron on the periodic table. Already we found it. And that's going to be 55.85. And you're going to get another iron value. And you're going to compare the two. The lowest iron value is the one that's going to be the amount you can actually make. And that's because, like with the sandwich example, the other thing is going to run out. So the math here is going to be 175 times 2 times 55.85, all divided by 280, or 28.0 times 3. And we get that we could make 232.7 grams of iron based on this amount of carbon monoxide. The important thing is that you recognize that you got to compare these two values and you got to pick the lower one. So the bread example, if we had 8 slices of bread and 3 pieces of tomato, we could make 4 whole sandwiches based on the amount of bread we had. We can only make 3 whole sandwiches based on the limited amount of tomatoes we had. Because this given amount of iron is going to cause us, or this given amount of iron 3 oxide is going to cause us to make a lower amount of iron because it's going to run out first. It's our limiting reactant or limiting reagent. The limiting reagent is the Fe2O3 because when you do the stoichiometry with it, it's the one that gives you a lower amount of possible iron. The excess reagent is going to be the carbon monoxide because when you do the stoichiometry with it, you theoretically could make a greater amount of pure iron. But if you have these two things, this limited amount of iron and this limited amount of carbon monoxide, this limited amount of iron oxide, I should say, and this limited amount of carbon monoxide, it's this value that causes you to make less iron, and that's why you choose this answer for the possible amount of iron you can make, which is 157 grams.